Looking at section 4.7 and the first part of 4.8, what we're going to be talking about is remember we're in applications of the derivative, and an interesting problem in mathematics is finding where functions cross the x-axis, finding the roots of functions. Now, you know, for a quadratic function, you can always use a quadratic formula to figure out where it crosses the x-axis or factor it, but you can absolutely solve it. And it turns out that a cubic, a quartic, and a quintic have really scary formulas, but they also can be solved without calculus. And that was in the 14 and 1500s that those formulas were discovered by different mathematicians. And there's actually some interesting stories about duels between mathematicians and how they at the time you would have your position as an instructor at a university, but you could be challenged at any time by some, rogue mathematician that wanted your job. And so you always kept in your back pocket like some formula that you'd come up with or something. And so solving the cubics and the quintics and that sort of thing was a big advance, but it was kind of before information was considered important to be shared. The people were still very protective of their work. But there are higher degree polynomials and exponential functions and different types of functions where finding where they cross the x-axis is not immediately possible to do, and so you have to use approximations. And Newton gave us one of the first approximations with tangent lines that is really clever and cool, and what we're going to look at right now, it's called Newton's method. Now, your graphing calculator probably doesn't use Newton's method because you can actually take courses on all different types of numerical methods, and there are methods that are more that are quicker and that find the zero faster than Newton's method. But it's easy to look at, and it's one of the first ones. So let's go ahead and get started. Oh, wrong button, sorry. Okay, so this is a graph that I want to look at. Right here, this function in blue is y equals f of x, and we want to find where it crosses the x-axis right here, all right? And so my function is x cubed plus 4x squared plus 7x plus 3 equals 0. And I want to, or that's my equation, I want to figure out where that equals, where that is true, where that equals 0. Okay, and what we will do is we'll say, well, let's just pick a point, just an arbitrary point, and let's find the tangent line at that point. And let's see where that tangent line crosses the x-axis. And because obviously a line, you can always figure out where it crosses. You just set it equal to 0 and solve it, to figure out where it crosses the x-axis. So you randomly choose a point, and there are some strategies on what point to pick. But anyway, you randomly choose a point, and then you find the equation of the tangent line, and you figure out where that tangent line crosses the x-axis, and then that place is going to be your new point that you will use. Then you will find the tangent line at that point, see where it crosses the x-axis, and you repeat the process over and over again until you eventually get very close within a few, as accurate as you want to where it crosses the x-axis. So your coordinate will get closer and closer to the value that you desire. So what we'll do is we'll find the slope at at what we call an initial or starting point. And you can just kind of guess it. And so how do we find the slope? Well, so we'll solve that initial point will be x naught. Of course, the slope then will be f prime at x naught. We'll just take the derivative and plug in the point. All right, then we remember our equation of a line, y minus y1 equals m onto x minus x1. So let's write it in terms of the notation that we have. It would be y minus f at x naught equals m onto x minus x naught. But I shouldn't have written m. Instead of writing m, I can write f prime at x naught. So that looks scary, but that's just your equation from college algebra. You know that y minus y1 equation. All right, now remember you're looking for the x-intercept on this equation, so you're going to plug 0 in for y and solve for x. So we're looking for the x-intercept of this line, and so we will plug 0 in for y and solve for x. Okay, so you'll have 0 minus f at x naught is equal to f prime at x naught times x minus x naught. And so the first thing you might want to do is divide by f prime at x naught. And then you can just move the x naught over, and so you get x naught minus f at x naught over f prime at x naught is going to give you x, the x-intercept. Well, what we'll do then is now we will use this value and repeat the process. Okay, so let me see if I can emphasize this. We picked x naught, our first point, and we came in here and we found the equation of the tangent line, and we found where that tangent line crosses the x-axis. We used this new x-coordinate, which is the x-intercept of the tangent line, to go back up to the original function and find an equation of the tangent line at that point and see where it crosses the x-axis. And then we'll do it again until we get close enough, as close as we want, to the 0 for the function. Okay, so your procedure then is to guess a first approximation to a solution to the equation f of x equals 0. And if you look at the graph, it helps. Now, of course, if you look at the graph and you probably are going, well, why don't I just do second calc 0? I mean, you know, you can use your calculator, but we're doing it old school. All right, and then you use the first approximation to get a second, the second to get a third, and so on using this formula. X sub n plus 1 is equal to x sub n minus f of x sub n over f prime at x sub n. So this is called a recursive formula. And it uses the previous to get the next. So when I'm talking about this, I'm going to say xn, I'm going to call that the previous, and x sub n plus 1 is the next. And I'll write it again just because it's kind of fuzzy on this paper. X sub n plus 1 is equal to the previous x coordinate minus the function evaluated at that x sub n over the slope at that x sub n. Okay? Of course, the derivative cannot equal 0 because that would mess this up. Okay, so let's use Newton's method to estimate the solutions of the equation x cubed plus 3x plus 1 equals 0. And they give us the initial value, and they just want us to find x2. So let's see if we can go through the process here by hand. All right, so the first thing we know is that we need to figure out what the derivative of this function is, which is just 3x squared plus 3. Okay? And we'll need to compute f prime at x naught, which will be f prime at 1, and that is just going to be 3 times 1 squared plus 3, or just 6. And we will also need f at x naught, which is 1. F at 1, sorry. And so that's going to be 1 cubed plus 3 times 1 plus 1. So that's going to be 5. Okay? And so what we do then is we say the next point, x sub 1 is going to be x sub 0 minus f at x sub 0 divided by f prime at x sub 0. So it will be, in this case, 1 minus 5 divided by 6, or 1/6. And then this is what we will use to find x sub 2. X sub 2 will be 1/6 minus f at 1/6 over f prime at 1/6. So that'll be 1/6 minus, okay, f at 1/6 is where I'm going to have to start using my calculator. So let me show you. If we do 1/6 cubed plus 3 times 1/6 plus 1, we get that, and we can math frac that probably. So 325 over 216, 325 over 216, and then we'll put 1/6 into the derivative, which will be 3 times 1/6 squared plus 3. We can math frac that. 337 over 12. Okay, and then, so this will be, we can do 1/6 minus 325 divided by 216, and then we're going to divide that by 37. Oops. $37 divided by 12. And we get that. We can math frac that. So negative 107 over 33, or negative 0.321. Over, what was it? 333, which is negative 0.32. Okay, so that's all fun, but yeah, okay, I don't want to do that. That's too much work. So let me show you some quick tricks on how to do this with your graphing calculator. And this is actually still a little bit of work. You could actually write a program to do this, but I'm going to give you kind of the ideas of it. What you want to do is put the original function into y equals. So we'll do x cubed plus 3x squared plus 1. We'll stick that into y equals. Now, you can go ahead and put the second derivative into y2, or your calculator, I haven't showed you this because, you know, I didn't want you to know, but your calculator will actually compute a derivative for you at a particular point. And so you can do math, and then if you go down and you pick choice 8, which is the derivative, and derivative, and then you can tell it to compute the derivative. It won't give you the algebraic. It won't give you 3x squared plus 3, but it will give you, at any particular value, it will give you the derivative of a function. And the way you enter it in, there's a command here. You have to tell it what function you want to take the derivative in of. So you could either type this function in, or since this function is programmed into your calculator, actually, I want to, in this screen, yeah, it's fine. How I'm doing it's fine, I guess. Okay, let me just say something. Actually, in one line, I want to get this command here. So I'm going to do this. I'll show you that end derivative in just a second. I'm going to type in this x1 equals x naught minus f of x naught over f prime of x naught. So I'm going to do x minus f at x naught is my y1. So I hit the vars button, and then I go over to y vars, and then choice 1 is function, and you can grab any of your previous functions. So I'm going to grab y1. And then I'm going to divide that by now the derivative of y1. So now I'll do math, and then choice 8 was the end derive, and I have to do of what? So I have to do vars, and then over to y vars, and then function, and then y1. So you tell it what to take the derivative of, then you do a comma, and you always say with respect to x, so I say comma x, and then you tell it where you want it to take the derivative. In this case, it's actually at the x that we're going to give it. So we're going to say comma x, comma x. And then, did you guys, those of you that are trying, did you type this into your calculator? Because it's kind of fun. I don't know. Are you okay? Anybody? Just watching it. You can even check it on the video later. Okay. So then what happens, let me just kind of verify one thing for you. If I did math and then choice 8, the derivative of like we know that the derivative at 1 was 6. If we do, we can type this in, x cubed plus 3x plus 1, and we say comma x, comma 1, and hit enter. It should give us the answer of 6. Now, it doesn't give it exactly because it's an approximation, but it's pretty close to 6. All right, so that's all the derivative function will actually, when you type it in the end-derived function, you type in the function, you always have to say comma x, and then you put the point that you want in. Now, the reason in here that I put comma x is because I'm going to be changing my x each time. Okay, so now if I want to go through the process to figure out what x1 is, I need to store what x naught is. Now remember, we chose x naught to be 1. So I'm going to take 1 and I'm going to store that in x. All right? And then now I have the program programmed into y2. I have where you do x minus f prime of x over, I have Newton's method, x naught minus f of x naught over f prime of x naught programmed into y2. So I'm going to grab that by going vars, y vars, function, and then I grab y2, and I hit enter, and what it's going to do is it's going to evaluate the function, it's going to evaluate that equation, x naught minus f of x naught over f prime of x naught, at the point when x is 1. And see, if I math frac this, I don't know if it'll do it for me, but it can't. But 1/6 is basically that. See?
Can you also look at the table?
Yes. Yeah, you could go to the table, and you could put 1 in there, and you would get the same number. But you need to be looking at y2. Okay. Now what I want to do is store this answer that I got. Let me do it again. Let me do it all again. So once you have it computed in, all you have to do, now that we have this generic formula in y2, all you'll have to do for the homework is just change your y1 equation. Does that make sense? Each time, because the formula is in y2. So, and then what you do is, I just hit clear. So you type the function into y1. And then in the home screen, you're going to store whatever your initial value is in for x. So I did 1, and I stored that in x. Then I asked the computer to evaluate the equation that I put into y2 for that x value. So I do vars, y vars, function y2, and I hit enter. Now what I'm going to do is I'm going to store this number in x, because that's my new x. So I'll store that in x. And then I repeat the process. Now you can do vars function, vars, y vars function. You can do that, or you know how the second entry will let you actually pull up your previous command so you can get the y2 right there, and then hit enter. And see that negative 0.321, that's this number that I got here when I did it by hand. Are you following? With the video, maybe. Do you want me to go back over it? Or Robinson, did you get it at all? I can't tell.
Yeah, we got it.
Okay.
Yeah,
okay.
we got it.
I know, it's fun with the calculator. Okay. And so then what you can do is you can keep doing this. So you could store this in x, and then you could do it again. You could ask for y2 again. And what's going to happen, then you could store that in x. And you could do it again. And you're going to close, notice how close they're getting. They're within, see how it was negative 0.321 and then negative 0.32218, you know, and see how close they are?
Just recomputing it.
Right, and it's going to get closer and closer to the true value. Now you're within 1, 2, 3, 4, 5, 6 decimal places of the true value. So I know this really takes all the fun away, but if you go to the graph of this, so I'm just going to take this off, and if you graph this function, and you wanted to find that 0, you know, you go to the left, and then you go to the right, and what's it going to be, probably? Negative 0.322185. So do you see it's doing it for you, it's computating it for you. So I don't think that your calculator actually uses Newton's method when it goes to find the 0, but you did notice how it asks for a bound between a left and a right, you know, interval, and that's kind of the same. Your question may be, how do you know where to start? And there's some techniques. I mean, it's a whole other course on numerical methods. So I'm just kind of wetting the palate here, getting you interested in a application of Newton's derivatives. Okay, so let's try another one. It says, use Newton's method to find all the roots of the equation e to the negative x minus 2x plus 1 equals 0. Okay, so it should be minus 1. I should correct it here. E to the negative x. So this is going to be minus 2x plus 1 equals 0. Sorry. This is what the first thing you do is write that equation, and this will be your f of x. So now that we have our graphing calculators that we can use as tools, let's go ahead and do this with our calculator. So I'm going to go to y equals, and I'm going to type just the function in to y1. So I do second e negative x minus 2x and then plus 1. Now, in order to get a place to start, I'm just looking and I see the graph and I think, well, it might be smart to start at about 1. It looks like it crosses somewhere close to 1. Does that make sense? So I'm going to choose from the graph my starting point to be 1. No, see, it's crossing right here. We're looking for where it crosses the x-axis, so it seems to be crossing right at about a little to the left of 1. Are you with me? Okay. So I'm going to let x naught equal 1, and that's sort of arbitrary. Sorry, things are going crazy. No. Why did they all went... What's going on?
Put your hand on it.
Well, I hit this one little button and it goes crazy on me. Okay. All right. This is it's like a ghost problem. Yeah. Why is this one blue? I don't know. Okay. So x naught is 1. So I'll go to my calculator and I'll do store 1. So I hit the 1 and I'm going to store that in x. And then I grab my y2 command, and this number, 0.7330436, will be my x1. Just a second. 0.7330436. Okay, and so you hit this STO button, so it's going to store the answer in x. So I just hit the x. And you have to hit enter to execute that. And then I'm going to call y2 up. And hit enter. And I get 0.7388318. Does that make sense? $88318. And I want it correct to 6 decimal places, so I'm going to stop when I get the decimals to match to 6. Okay, so now I will store that in x, and I will use that in y2. So I'll call y2 up and get it to evaluate. See, I'm getting really close. Now I'm to 5 decimal places. 1, 2, 3, 4, 5, right? 0.73883. So this is the third one, 0.73885. So I'll store this in x, and then I will call y2, and have it evaluate there. And now I am close enough, very close. And look how close I am. That's pretty interesting, huh? So I get 0.738835 is 0.311. That's close. That's accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places. Okay. Yeah. So x sub 3 is 0.738835. So I'm good to go. Okay.
I'm getting rid of the decimal on here. Like every time like 1 plus 1 equals 1 bunch of 0.
Oh, okay. So under mode, change it to float.
Float?
Yeah.
Okay.
You must have 9.
6.
So yeah, because it's showing you 6
Yeah,
decimal
6
places.
0. Okay. I just didn't know what was that.
Okay, so that was fun. Wasn't that fun? Are y'all? That's it. That's it for 4-7. That's Newton's method. Did y'all get it?
When I did my calculator, I got an error called something like that.
Yeah, it's probably. Do you want to go? Does anybody want to go back over it with their calculator? Do y'all want to practice it one more time with your calculator? Yes. Okay. The big thing is go to your y equals. Make sure you have the equation, the second equation in y2, in there correctly. You do x minus y1 divided by n derive y1 comma x comma x. Do you guys know how to find all those? You came in kind of late. Or do you want me to go back over how to grab it? Okay, I'll just clear this out. Okay, so you do x minus y1, which you grab by doing vars, and then y vars, and then function, and then y1, and then divided by, and the derivative lives under the math function, so you do math, and then it's choice 8. And you want to take the derivative of y1, so you go vars, and then over to y vars, and then you hit the function, and then the y1. Are you with me?
Yeah.
And then you do comma x. You always, if you're doing that, you always do comma x. And then normally you would do comma wherever you want, like whatever number you want, like 5 or 12 or whatever. But here we're just going to do x because of the nature of the way that we're doing it. And then you'll always put your original function in y1, or whatever the function is that you're trying to find the 0 for.
Okay, comma, where's the comma?
It's above the 7. Okay? And do you want to try it with this first function, e to the negative x minus 2x plus 1? You want to go through the process? Do you have that in y1? No, you're good. You feel okay. Yeah, and actually, if you leave this equation in y2, like just leave it there, then you'll always be able to use it.
Oh, you're using alpha x, so I'm just using.
I'm using this x. Good question.
Okay.
The x to the right of the alpha.
Would it matter what x you use?
I think it does, actually. Yeah. This x right here. To,
It means different?
yeah, I think it will. Were you using alpha x? I'm not sure. It might work. You could try it. You'll need to store it in alpha x. You could. Did you do one? Did you put the first equation into y1? What equation do you have in y1?
No.
Oh, well, you have to have something in y1 in order to do this.
Yeah.
Well, let me move on to the rest of the lesson, and then we'll look at this.
Just try to.
Yeah, practice it, because it's on the video, so you can practice it. Okay, now we've moved on. We finished 4.7. We're going to move on to section 4.8, and I broke this into a couple of parts.
Take it back.
Ms. Brooks, we have to go.
Oh, I'm sorry. Okay. A function f is an antiderivative of f on the interval if, when you take the derivative of big F, you get little f. You get this original function for all x in the interval. So basically, this is the idea where we undo what we done did. And so, like, if you know that the derivative is x squared, then you know the antiderivative, we've kind of talked about this at the very beginning of this chapter, would be x cubed over 3, right, plus some constant. Because you could take the derivative of 5 and it's just 0 and you wouldn't know. So you end up with a family of functions. This function, which is called the antiderivative, is actually a family of functions. So f prime of x, notice, is x squared, which is little f of x. So this antiderivative has the property that when you take the derivative of it, you get to the little f. Okay? Well, it turns out, if f is an antiderivative of the little f on the interval I, then the most general antiderivative of f on I is just add this constant c. So plus c. All right, so that sounds good. Now, we have this sheet here which gives us some basics, and we've already looked at this, basic functions and their general antiderivatives. And I like this sheet okay. I like the big derivative and integral sheet better, but I'm not really ready to talk to you about how to use the integrals yet. So we'll just use this sheet for now. But we kind of looked at some of these already. Do you guys remember talking about the sine? We knew its antiderivative would be negative cosine kx over k. So for the sine of kx, or that you'd add 1 to the exponent and put it over it. This was at the the first section in this chapter. Okay, so we have these antiderivatives, and some of them you're not going to use, the scarier cosecant, inverse tangent, all that. We won't use those just yet. Let's see. So what do you think the antiderivative of 6x is? Well, the constant always just tags along. And so it's going to be 6, and then according to the first one on the table, it says that if the function is x to the n, the antiderivative is 1 over n plus 1, x to the n plus 1. So this is understood to be x to the 1. So it's going to be 1 over 1 plus 1, x to the 1 plus 1, plus c, or 6 times 1/2 x squared plus c, or 3x squared plus c, right? And you could probably have stared at that one and figured out what function has as its derivative 6x. Most of y'all are probably going to tell me 3x squared without me having to go through the formula for you, right? But I go through the formula for when it becomes more complicated. Okay? So this function, 3x squared, is the antiderivative of the function 6x. When I take the derivative of 3x squared, I will get 6x. So we're going backwards. All right, so for x to the 7th, the antiderivative, I'm still going to use the first formula. It'll be 1 over n plus 1, where my n is 7. So 1 over 7 plus 1, x to the n plus 1, 7 plus 1, plus c. So this is 1/8 x to the 8th plus c. And remember, you can always check these, because you can take the derivative of your answer, and you should get back to the function that you were given. If you take the derivative, the 8's cancel, and you just get x to the 7th. Okay? All right, so what will this one be? Well, now we're probably about ready to put some things together here. The antiderivative of x to the 7th is going to be 1 over 7 plus 1, x to the 7 plus 1. So 1/8 x to the 8 minus the 6 tags along. The derivative of x is the antiderivative of x is x squared divided by 2. And then what's the antiderivative of 8? What function has as its derivative 8? 8x, good. And then plus c. And then you can clean this up. 1/8 x to the 8 minus 3x squared plus 8x plus c. Okay? All right. This one is a good idea to write this as 3/2 x to the 1/2. And 1/2 is your n. Okay? So big F of x, which is called the antiderivative, you're going to add, the constant just tags along, so I'm just going to write it, 3/2. Then you do 1 over n plus 1, so this is 1/2 plus 1, x to the 1/2 plus 1. Now, I don't normally show all of this work, but while we're first doing this, I think it's okay. All right, so in your denominator, 1/2 plus 1 that's 3/2. And so when you flip it, it's going to be 2/3. So this is going to be 3/2 times 2/3 x to the 3/2 plus c, which is just then x to the 3/2 plus c. Okay? All right, and this function, this 1/2 is just tagging along. You need to think of this as 1/2 x to the negative 1/2. Does everybody agree with how I wrote that? All right, so big F of x, this negative 1/2 is your n, right? You write your constant that tags along times 1 over n plus 1, so negative 1/2 plus 1 x to the negative 1/2 plus 1 plus c. All right, negative 1/2 plus 1 is 1/2. So this is 1/2 times 1 over 1/2, which is 2 over 1, x to the 1/2 plus c. And so this is just x to the 1/2 plus c, or the square root of x plus c, which should feel pretty good because you can check these right away. The x to the 1/2, if you take the derivative of that, it's 1/2 x to the 1/2 minus 1, 1/2 x to the negative 1/2, which is what we started with. So they're self-checking if you are good at your derivatives. Okay, so we would think of this as x to the 1/2 plus x to the negative 1/2. So our general antiderivative, we will add 1 to the exponent, and we'll do 1 over 1 plus 1/2, or 1/2 plus 1. It's n plus 1. X to the 1/2 plus 1 plus 1 over negative 1/2 plus 1 x to the negative 1/2 plus 1 plus c. And then this cleans up. This is 3/2 in the denominator, so this is 2/3 x to the 3/2 plus, this is 1/2 in the denominator, which is 2x to the 1/2, and then plus c. Everybody happy? All right, let's try this one. This is x to the negative 1. Can we use add 1 to the exponent and put it over it? If our x is negative 1 and we add, that's going to be 1 over 0, right? So that's not quite going to work. Do we have a function on our table that might work? Do y'all see a function on the table? Right. And you may have already been thinking the function that has as its derivative 1 over x is the natural log. I don't know if you remember that. But anyway, it's going to be the ln of the absolute value of x plus c. So that is what we will have here. So use number 9 on the table. And so you're going to get the ln of the absolute value of x plus c is your big f of x. Okay, and so for these others, these are kind of going to be straightforward. This constant 7 just tags along, so you can think of this as 7 times 1 over x. So this is going to be 7, the antiderivative is going to be 7 times the ln of the absolute value of x plus c. Okay? And here, what's the antiderivative of 1? What function has as its derivative 1? Just x. Minus, this will just be 5 ln absolute value of x, and then plus c. Everybody okay? All right, well, what about the sine function? Well, yeah, we have a rule for the sine function. The antiderivative of sine kx is negative 1 over k cosine kx plus c. So it should be negative 1 over k cosine kx plus c if the sine of kx is f of x. Then your general antiderivative, big F of x, is this. Okay. K is the constant in front of the x. So here our k is pi. Okay? Now this negative pi is just tagging along. So you're just going to write it. You're just going to let that negative pi tag along. So this will be negative pi. And now let's just think of the antiderivative of sine pi x. Well, it is negative 1 over k, where the k is pi, cosine pi x, or kx, which will be pi x, and then plus c. And then we can notice here our negatives cancel and our pi's cancel, so we get just cosine pi x plus c. You see how I didn't let this pi at front bother me at all. I just let it tag along, and then I cleaned it up at the end. Okay? Just like I'm not going to let this 3 bother me, okay? Here your k is 1, right? So big F of x is going to be, just let the 3 tag along, and it's negative 1 over 1, so we don't need to write that. Negative cosine kx, well, k is 1, so just x, plus c. So this is negative 3 cosine x plus c. Okay? And so then now this one, all right, this is my k. So this is going to be negative 1 over k cosine pi x minus the 3 is going to tag along times the k is 3 now. So this is negative 1 over 3 cosine 3x plus c. This will be my big F. And so, oops, I put a k there. I meant a pi. Because k was pi there. So this is negative 1 over pi cosine pi x, and this will become plus cosine 3x, and then plus c.
Would it be 3? Would that be a conflict? Oh, no.
What did I do? I was working on this one, and the k for this one was 3. Where, do I have a mistake somewhere? Right. That's the antiderivative. Yes?
So, what happens to the 3?
Well, the 3 here and a 3 and 1/3 there are canceled. You with me? Okay.
Yeah, that's not just
All right, now, what function has as its derivative cosecant x, cotangent x? Well, you might kind of remember, but if you don't, you can go up and look. Cosecant kx, cotangent kx is negative 1 over k cosecant kx plus c. Okay, so it's the negative cosecant with dealing with, in this case, we don't have a k. K is 1 here. So this is going to be, the general antiderivative is going to be negative cosecant x plus c, because our k is 1. All right, and so then again on B, notice on B, we have this negative that's going to tag along, and the 5 is our k. So the antiderivative f of x, the negative tags along, then it's negative 1 over 5 cosecant kx, which is 5x plus c. And then those negatives cancel, so it is positive 1/5 cosecant 5x plus c. You okay? All right. Pi x over 2. All right. That is, the k here is pi over 2. And this negative pi is just tagging along. All right. It's a Girl Scout cookie. All right. So f of x is equal to the negative pi, which is just tagging along, and then the antiderivative of cosecant cotangent is negative 1 over k, where k is pi over 2, and then it's cosecant kx, which is going to be pi x over 2, plus c. All right, now the negatives will cancel. I'll flip this and notice that the pi's will cancel. So this is going to be 2 cosecant pi x divided by 2 plus c. And remember, you can always check these. You can take the derivative to check and see if it's correct. All right. Now we have a family of e's, it looks like. So let's go up to our table and see what the antiderivative e to the x is. I bet you probably know. The antiderivative of e to the x is e to the x because that's the special e to the x function. But if you have e to the kx, it's 1 over k e to the kx plus c. Okay? So here your k is 3. So f of x, big F of x, is going to be 1 over 3 e to the 3x plus c. Here your k is negative 1. So this is going to be 1 over negative 1 e to the negative x plus c, or just negative e to the negative x plus c. Here your k is 1/2. So f of x will be 1 over 1/2 e to the x over 2 plus c. And you can flip that. It's going to be 2e to the x over 2 plus c. Uh-oh. That one looks scary. So probably there's a formula. I think it's an inverse sine. Let's look. Yes. 1 over the square root of 1 minus k squared x squared is 1 over k inverse sine kx plus c. Okay? So I'm going to go ahead and write that one down. One over the square root of 1 minus k squared x squared, if that's your little f of x, then its antiderivative, big F of x, is 1 over k inverse sine kx plus c. Okay, and then our k here is 1. What is the 2 doing? It tags along. All right, so don't worry about the 2. So f of x is equal to 2, and then it's going to be 1 over k, which is just 1, inverse sine kx, well, k is 1, so just x, and then plus c. So you can just say 2 inverse sine x plus c. You don't have to like distribute the 2 onto the c because it's just a constant, whatever, 2 times the constant. Okay, it doesn't matter. Okay, this is the inverse tangent function. You should have this one memorized. It shows up in your life a lot. You know, like you're just walking down the street, bam. So if you have this function, f of x equals 1 over 1 plus x squared, know that its antiderivative is the inverse tangent function. So this is 1 over k inverse tangent kx plus c. How are we doing with this formula stuff? Because this is the work of engineers, right? This is what engineers are doing. It's like they can't remember anything, but they have a table, they have a book, they can interpret formulas. So that's what I'm trying to practice with you guys. Okay, this is the formula. How does that apply to my problem right here? Does that make sense? So you're going to have to fit your stuff into the formula. Obviously here it's kind of switched around, right? And you know that the 1/2 is just a tag along. So for this one, it's going to be f of x is 1/2, and then it's going to be inverse tangent kx, where your k here is the coefficient in front of the x, which and it's the square root of the coefficient in front of the x, which is just 1 here. So it's going to be x plus c. So this was very exciting. All right, this one's more exciting, right? Because this is k squared and this is x squared, right? So you have to recognize that k on this one is 2, not 4. Okay, and so it's going to be 1 over 2 inverse tangent 2x plus c, using the formula. Okay. All right, this is really fun because you get to learn a new symbol, right? All right, if we want, before I just made a big sentence, I said find the antiderivative. You know, that was the directions on all of those, and that's why we're doing the big F. But I used big F, that was my antiderivative. Well, there's actually a symbol that says what is the antiderivative. Just like there's a symbol that says take square root, you know, the little square root symbol and different symbols. So this symbol right here, this little s, is called the integral, and it means find the antiderivative. So when you don't have, and we will in the next chapter have numbers here and here, but when you don't have numbers there, it's called an indefinite interval. And the reason it's indefinite is because we can't get there exactly because we have that plus c. Okay, of this little function f with respect to x, the symbol, this integral symbol is called the integral sign. The function is called the integrand of the integral. It's just like you have a divisor and dividend and all that. And x is the variable of integration. So this dx means what you're taking the integral with respect to. So all this really is a way to ask you to find the antiderivative of the little part right here. So this is saying find big F of 5 minus 6x. It's a new formula, or new symbol to do that. Okay, and so this is, what is the antiderivative of 5? 5x. What is the antiderivative of 6x? It's 6x squared divided by 2. I think I heard 3x squared, which is right. And then plus c. So we can clean this up as 5x minus 3x squared plus c. So we're just doing what we were doing. I just introduced this new symbol to you. Okay? So on this one, what I would do, I always like to clean them a little bit before. So I would write this as x to the negative 2 minus x squared minus 1/3 dx. Now, when you find the antiderivative, the little symbol goes away. It's tempting to write it because it's cool and you haven't written it in a while. But once you do the antiderivative, you don't write the symbol again. So, yeah, this is going to be x to the negative 2. You add 1 to the exponent, so that's going to be x to the negative 1 over negative 1, negative 2 plus 1. Minus, this will be x squared over 2, and this will be minus 1/3 x. And then, oh, yes, thank you. And so then this is x cubed over 3. Okay, and then you can clean this up a little bit. This is negative 1 over x minus x cubed over 3 minus 1/3 x plus c. Everybody good? See if we have another one. Oh, no, that's it. So we're just going to be doing more of these in the part 2 of it. So on Friday, we're just going to do lots more examples. Integration, finding antiderivatives, is inherently harder than differentiation. For example, there are courses in college called ordinary differential equations, ODE, partial differential equations, PDE, just differential equations. These are courses, there's 3 courses I've just listed, just trying to find antiderivatives. So it's,
oh my God.
Yeah, it's much, what I've shown you right now, you're like, oh, this is easy. Well, we could probably in a second come up with a function that we can figure the antiderivative
And that's
out.
a differential equation?